the rigid guides given in the both side, so it can only translate. So this is called a radial translating follower. Now we move to the next category of follower, which is called flat facing, flat translating, sorry, which is called offset translating follower. So offset translating means the follower will translate, but it will have the line of this translational motion does not pass through the center of the hinge point of the cam. The example is given here. So here you see the follower. This is the flat face follower. We'll come to that. It is called flat face follower. This is a follower which can go up and down. So the motion, so the line of motion of this follower is just a straight line. This straight line, but you see this straight line is not passing through the hinge point of the cam. The hinge point is here. So if we draw a straight line which is just parallel to the translating motion. Okay, so the line of action, line of motion of this follower is this, and and if we draw a parallel line from the center of the cam or the hinge point of the cam, you will see there is a constant distance, and that distance is called offset. Okay, so this follower is called offset translating follower. Now we will take another example. Here you see there is a disk, and that disk is hinged at this point. We have another object which is a follower. This follower is hinged at this point. With the help of a torsional spring, we can always make these two objects always in contact. Now when this disk will rotate, what will happen to this object? This is the follower. This will have some oscillatory motion with respect to this hinge point. Then this follower, this kind of follower is called oscillating follower. Okay, and according to the nature of the surface which are in contact, according to the nature, the followers again classified as knife edge follower, flat face follower, roller follower, spiral face follower. For example, this follower, you see the contact point is a knife edge contact point. So this follower is called a knife edge follower. This follower, on the other hand, you see this is a follower. In this follower, the face is a flat face which are in contact. It means this contact point, not always this point. Contact point is sometimes this point, sometimes this point maybe. Okay, and this is a flat face. So this follower is called a flat face follower. And we have drawn another example here. Here you see this is a cam which is hinged at this point, and this is a follower which can go up and down, translating follower. But at the end of the follower, we have given a roller. Okay, this roller provides what? When you have a knife edge follower or flat face follower, there is always friction between these two things. Obviously, if you put a roller, there will be a friction between this cam surface and the roller surface, but the rolling friction is less than this sliding friction. So the frictional force is less for this case. To provide this facility, to provide this advantage, we can put a roller, and this follower is called a roller follower. Similarly, spiral face follower is there. I have not shown it here. Okay. Now cams are also sometimes plate cam. Sometimes they are wedge cam and cylindrical shape cam. So all the examples we have discussed, this one, this one, this one, and this one, this is a plate. Okay, as I said, this is a disc, this is a plate cam. All this case they are plate cam. And here there is a case where if the cam is like this, the cam can move in this direction. So it is like a wedge, and the follower can move up and down. Okay, in that case, this cam is a wedge cam. Now, let us take another example of cam. This is a cam where this is actually a cylindrical object, solid cylindrical object, like a shaft. On that shaft, there is a groove. We made a groove, and this groove is not exactly. This groove is not a circle. This groove is not a circle on the cam. That means the if you can make a groove which is just a circular groove, and the plane of the circle is perpendicular to the plane, sorry, perpendicular to the axis of this cam. But this case, the circle is little bit tilted, and so the groove is like this. Okay, and you put a slider kind of object within that group which is connected to this follower, right? So when this cylindrical object rotates, so that means this slider will this distance will never change. The slider has to go this way or that way because it has to stay in the groove. So this is a follower which is a oscillating follower, but the cam is a cylindrical cam. Example of cam follower mechanism, where you see this outer box. Okay, this outer box, this whole thing is the follower, and we have two bearings, two guideways are there. So this whole outer thing can have a translation in this direction. Either it will go to the left or it will go to the right. Okay, this whole thing can go like this. Within that, we have just fitted a disc. Okay, so this disc can rotate. This disc can rotate with respect to this box, this outer box. With respect to this outer box, this disc can rotate. Now we have hinged the disc not at its center, at an offset. At some point we have hinged the disc. So if the disc is hinged at other point, what will happen? When the disc will rotate, obviously this box has to move left or right. Okay, so in this case, you see the contact between the follower and the cam. This contact is always there. This contact will not miss because we have constructed it such a way that this disc is fitted within this box. Okay, so when the disc is rotating, whatever may be the motion of this box, but these contact points will never miss. They'll be always in contact. This kind of cam system is called positive acting cam. Why it is called positive acting cam? Because you don't need an external spring system so to ensure the contact, to ensure always there is contact. That kind of spring is not necessary here. In this case, the contact is made through this geometry. Okay, the contact is never lost. So that is why this is called a positive acting cam. Now we'll have some nomenclature of cam when we discuss cam or design and analysis the cam. So we will use some nomenclature. We must understand those nomenclatures. In this case, we have drawn a radial translating roller follower. Okay, radial translating roller follower and a cam. So in this case, the cam is. Are you guys with me in the class?
Yes, sir.
My voice is audible clearly?
Yes, sir.
Okay. So this is the cam, all other things, whatever we have drawn, I will discuss. But actually, this is the cam, this one. Okay, this line. This is the cam, and this cam is in contact with this roller here. Here you have a roller. That roller is attached to this follower. Okay, so when the cam is hinged at this point. Okay, the cam is hinged at this point. That means when you rotate the cam in this direction, what will happen? This is at the lowest position, but when you rotate it from this position to this position, the follower will not change its upward motion, because you see just this is just circular. So when you rotate from this point to this point, the cam is rotating in this direction. The cam is rotating and passing through this point up to this point. The follower will not have any motion. But when it crosses this point, when the follower will touch these points, the follower will go up. Okay, similarly it will go up, and this may be the maximum point, then it will go down. So this is the cam profile. Now the first definition we'll have here is base circle. What is called base circle? Base circle is the smallest circle that can be drawn tangential to the cam profile with center at the cam center. So we have drawn a circle, this green circle, which is tangential to the cam at this point, at this through these arcs, through this arc. This circle, green circle, is tangent to the cam profile. So the requirement cam base circle is the smallest circle that can be drawn tangential to the cam profile, and the center of the base circle is the center of the cam. Okay, so this is called base circle. Have you got it? What is base circle?
Yes, sir.
Okay.
Yes, sir.
Now we'll go to next definition, which is called trace point. Trace point is actually a theoretical point. This point is on the follower. Its motion describes the movement of the follower. So in this case, the trace point for this particular case, actually if it is a knife edge follower, then the contact point is the trace point. But when this is a roller follower, the contact point is not a fixed point, because the roller is always rolling. So then we take the hinge point here at the roller. So that point is the trace point. So again, it describes the motion of the follower. A point which describes the motion of the follower, that is called trace point. So for this case, this roller follower, the hinge point of the roller is the trace point. But for a knife edge follower, the contact point of the knife with the follower is the trace point. Okay. Now we go to the next definition, which is called pitch curve. What is pitch curve? So here we apply the principle of inversion that we have done for the synthesis or dimensional synthesis of mechanism. The principle of inversion, other than rotating the crank, we have rotated any other. So if you remember, we have done that. The fixed link is rotated, but all other links are. So what we did in inversion motion, you can fix one of the link, other links are rotated. Okay, so that is called inversion motion, and we apply here inversion motion. If we hold the cam fixed, this cam, you hold the cam fixed and rotate the follower in a direction opposite to the direction of cam rotation, then the curve generated by the locus of the trace point is called the pitch curve. For example, in this case, suppose this is the cam and we are not rotating the cam, we are rotating the follower. So at some instant the follower is here, at next instant the follower is here, at some instant follower will be here, at some other instant follower will be here. So this way you can draw all the followers position inverted motion and then draw the locus of the trace point. As I said, for this case, this trace point is the center of this roller. So then you join the center of the rollers at different position. So then you will get a curve like this. This curve is called pitch curve. Is it clear to you? Hello? Just you have to draw the inverted
Means that
position.
locus of trace point is pitch curve.
Yes. See, it's a why we say it's a theoretical point. It's a theoretical point because for roller follower you have some trace point. For knife edge follower you have another trace point. For flat face follower the trace point is different, right? So for flat face follower, if you just consider the flat face follower, what is the trace point? It is in contact here at this point, but as the cam is rotating, the contact point will move. Okay, so the trace point is not a fixed point here. Is it a fixed point? It is not a fixed point. So to get the pitch curve for this flat face follower, to get this pitch curve, what you need to do, you need to draw all the inverted positions of the flat face follower. We will have example. We will see how to draw the cam profile using a flat face follower. Then it will be clearer, much more clearer to you. So in this case, you see this is the contact point. And then as it is rotated, the contact point will move. So that point is not the trace point. We have to find out a point which is the trace point. And the trace point for inverted motion, you will draw at every instant, you will draw the position of the trace point. Then that trace points, those trace points are connected. A continuous curve is drawn, that is called pitch curve. Now we will have next definition, which is called pressure angle. This is a very important definition, which is called pressure angle. First I am reading, then I will discuss. The angle between the direction of the follower movement and the normal to the pitch curve at any point is called the pressure angle. Okay, so it is said that this is the angle between the follower motion and the normal drawn at any point of the pitch curve. Okay, so let us take this is the pitch curve. All right, now we draw a normal. We select a point here and draw a normal. This is the normal to this pitch curve. Normal means at this point a line which is perpendicular to the, locally it is perpendicular to this curve here. Okay, so that is the normal we have drawn here. Now the other line is the line of movement of the follower. So follower motion, this is a radial translating follower. That means the trace point here and the center, if you join and extend that line, this line is the follower motion. Okay, movement of the follower. As it is the case here, this is the trace point and this is the center. If you join and extend, this is the line of motion of the follower. For other case, suppose you take this point and if you join with the center and extend it, that means this is the line of movement of the follower. Similarly, we did it here. So this is the point, the trace point, and this is the center. You join and extend it. This is the line of movement of the follower. So line of movement of the follower and a normal drawn at that point on the pitch curve, the angle between them is called pressure angle. Similarly, we have drawn, you choose this point, okay? And what is the pressure angle here? So you just join this point and this point, extend it. So that is the follower movement line. And from this point, we draw a normal to the curve, angle between them. This is the pressure angle. Okay. Is it clear to you? What is the definition of pressure angle? So, pressure angle. Have you understood? Pressure angle.
Yes, sir.
Then comes pitch point, a trace point where pressure angle is maximum. So this angle, where this angle is maximum, just let us examine some points. So let us take this point, trace point. So what is the line of movement? This is the line of movement of the follower. What is the normal? For this point, the normal is also the same point. So same line. That means the angle between the movement of the follower and the normal is 0. So here the pressure angle is minimum. But if you take a point here, okay, you will have this angle. Just move to this point or this point. You see again the pressure angle is 0. So this way you will find some points where the pressure angle is maximum. Can you tell me how many maximum pressure angles you can get on this pitch curve? How many?
Two.
Two. Okay, so two maximum pressure angle you can get. So corresponding to this maximum pressure angle, on the pitch curve, you have a point that is called pitch point. Okay, this point on which a point on the pitch curve where the pressure angle is maximum is called pitch point. Okay, this point where pressure angle is maximum is called pitch point. The next definition is pitch circle. A circle passing through pitch points. A circle passing through pitch points with center of the cams as its center. Center of the cam as its center. The first requirement is the circle has to pass through pitch points. As you said that there are two pitch points. So suppose this is the point where the pressure angle is maximum and this is the point where the pressure angle is maximum. So we have two pitch points. So for a circle you need three conditions, 2 points and the center. So here the center is the center of the cam. So now if you draw a circle which passes through two pitch points and the center is the center of the cam, then that circle is called pitch circle. Okay, this circle is called pitch circle. And the next definition is called prime circle. What is called prime circle? The smallest circle that can be drawn so as to be tangential to the pitch curve. It is tangential, smallest circle, tangential to pitch curve and center as center of the cam. So where is the pitch curve? The locus of the trace point is the pitch curve. Okay, and we have to draw a smallest circle which is tangential to pitch curve. So this is the circle which is tangential here to the pitch curve. To the pitch curve, this circle is tangential here. This is the circle, and this circle, center of the circle is the center of the cam. So this circle is called, this is the prime circle. Okay. So these are the definition, nomenclature of a cam. Generally, when we'll analyze or synthesize the CAM profile, we'll refer to these definitions. Okay. We must discuss is the description of follower movement, or this is called displacement diagram. Generally, what happens when we will analyze this kind of system, we'll assume that the cam rotates with uniform angular velocity. Means, example, this cam rotates with uniform angular velocity. And what happens when this cam rotates with uniform angular velocity? What happens to the motion of the follower? So you see why we need a mechanism. Here it completes a mechanism like cam follower mechanism. Why we need a cam follower mechanism? So actually what happens, sometimes we need some kind of motion or some kind of output, which is related to the motion, circular motion. In this case, this cam is having the motion is a circular motion, and depending on the motion, we want to control something, or we want to have something where the motion, the circular motion is here is here converted into um, translating motion. And sometimes this continuous constant speed circular motion, from that constant speed circular motion, we want a translating motion or a oscillating motion, which is having some function. That means we want to express the motion of the follower as a function of the rotational angle theta. Okay. So, for example, you take the cases of an IC engine. Okay. Say, have you read about IC engine? Hello.
Yes, sir.
So in IC engines, if you see the mechanism, you will see that there are valves which has to open and close at certain point of time, right? There are valves which has to
Yes.
close and open. So those opening and closing of valves or the firing, everything can be made using this. Okay, so the exhaust valve opens and closes, the oil which is injected into the cylinder, all of those things depends on the motion of the shaft. Okay, so the shaft is rotating. At certain point, you want the valve to open. So how that valve will be open? So you can imagine a mechanism like this. The cam is rotating, and when it is rotating at certain point, suppose at this point you want the follower to move at a distance, so that uh, with some other mechanism attached to this follower you can open the valve. Okay, so that is why this kind of mechanism, or at some point of time you want to open the nozzle of the oil injection, so that also can be done using this cam. Nowadays, there are electronic mechanisms also, but basic of those things are here in this cam follower mechanism. So this is one example where we are saying on off a motion using this cam follower mechanism. But there are many other applications where suppose I need a motion which is a constant velocity motion, or which is a simple harmonic motion, or which is cycloid motion, or constant acceleration motion. All those motions can be obtained using a cam profile and follower. Those for which cam profile and follower system we can get a simple harmonic motion, or a cycloidal motion, or a uniform acceleration or uniform velocity, that we can design. We can design the cam for a particular application. Okay, so for that, we first need to analyze what is the motion of the follower for all those cases. So what we will now do is we will analyze the motion of the follower. This is called description of follower movement, which is also called displacement diagram. So displacement diagram means displacement of the trace point. Here see this y is a coordinate which is attached to the displacement of the trace point, and theta is the rotation of cam, which we generally take uniform throughout. But throughout the cycle of its motion, the rotation of cam is uniform. So the angular velocity of the rotation of the cam is constant. Now typically when a follower moves, suppose there is a translating follower, when it translate, generally it has four steps. In one step, the follower goes up, which is called a rise. So with theta, how y varies? It may vary, it may follow a curve like this. This whole portion of the motion of the cam with respect to the follower, this motion is called rise. Okay. Then at some point, there will be no motion of the follower. The cam is rotating, but the follower is not moving. That portion is called a dwell, DWELL, dwell. And there is a portion through which the follower will return to its initial position, that is called return. And then there is a portion of rotation of cam when there will be no motion, again no motion of the follower, that is called dwell. So these four steps would be there in one cycle of cam rotation for the movement of follower. Okay, first is rise, then dwell, then return, and again dwell. So you can understand from this example also, when the follower is moving from this point to this point, the path is circular. You see, that means there will be no motion of the follower when it is touching these points. Whereas when it is on this, the follower will rise, rise. But here again, you see this portion of the cam profile is uh, is uh, is having the curvature whose radius is this only. Then when the follower is moving from this point to this point, so again there will be no motion, no translational motion in the follower. And then when the follower moving on this, it will go down, down, and there is the minimum position of the follower again. And that continues with each cycle. Okay, now we will see what are the different kinds of motion which is possible in this during this rise or during this return. We will just discuss the motion during rise, which is easily applicable for this case return. Okay. Now this is where we will actually discuss four kinds of motion of the follower, and these motion are uniform velocity motion, simple harmonic motion, uniform acceleration, which is also called parabolic motion, and why it is parabolic we will discuss, and cycloidal motion. These four kinds of motion of the follower we will discuss. Actually, what we will do, we will find out what is the relation between y and theta. We'll find out equation of motion. Okay, the relation between y and theta. So for uniform motion, we'll find out the relation between y and theta. For simple harmonic, uniform, and uniform acceleration, and cycloidal motion, we'll find out what is the relation between theta and y. Actually, we want to find out y as a function of theta. This is what we want to find out for all four cases. Okay. What is the advantage? Why we need to find out this relation? Because when you have a relation which is y is equals to as a function of theta, then you can find out once you have the displacement, then you can find out from this equation what is the velocity, what is the acceleration, and higher order derivative, like if you take derivative of acceleration, that is called jerk. Okay, we need to check all those kinematic quantities, because if we don't know those kinematic quantities, as you know that the force applied is proportional to the acceleration, okay, velocity. So everything we need to check whether that is fulfilling our requirement or not. To ensure that, we need to find out this mathematical relation between the cam rotational angle and the displacement. Once we get that, we'll take derivative of that, we'll get velocity, derivative of that, we'll get acceleration, derivative of that, we'll get jerk. Okay, so for uniform motion, suppose the first case we are discussing uniform motion. Uniform motion means uniform velocity. Uniform velocity of what? The follower motion. Follower is moving uniform with uniform velocity. The cam is rotating, the follower is moving with uniform velocity throughout this rise. Okay, so 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 we need to express y equals to f theta. Okay, so if you take derivative y dot, you know, derivative with respect to time, so y dot is equals to, here in this case you have to take derivative of f with respect to theta and then derivative of theta with respect to time. That's what we did here. What is this means? This f dash means derivative of f with respect to its argument. Okay, so we have this. Now for uniform velocity, y dot is the velocity, uniform velocity uh, of the follower. That means this must be equals to constant. Already we said that this theta dot is a constant. Okay, because the cam is rotating with uniform angular velocity. This is the angular velocity of the cam. This is a constant. That means this f dash theta has to be a constant if we have a uniform velocity motion of the follower. Now, if this y dot, let us take this f dash theta, which is a constant, that is designated by a symbol c. Okay, this constant is c. So our equation is y dot equals to c into theta dot. Now, if you take, we want to go back to this relation and we want to find out what is this. So to find out that, let us start from here. Okay, y dot equals to c into theta dot. Y dot equals to c into theta dot. Both of them are constant in this right hand side. Now, if you integrate it, what you will get? You will get y equals to c into theta plus a integration constant, right? Just y dot equals to c theta dot. So if you integrate it, in the left hand side you have y, right hand side you have c theta plus a integration constant. That's what we have written. Now let us check the condition of this motion. If it is in uniform motion, started from this point, okay? Started from this point and it is in uniform motion. Okay, this is the y-axis. The maximum point, the maximum movement of the follower during rise, this portion of the follower motion is called rise. From the minimum position to the maximum position, the follower moved from minimum position to maximum position. This is called rise. Okay, this maximum rise is called lift, L, lift, and the angular rotation of the cam during this rise generally designated by theta Ri. Okay, so when theta equals to 0, the follower was at 0. When theta equals to theta Ri, that means the maximum rotation of the cam after the end of rise. What is the displacement? Y equals to L. So if we put here that condition when theta equals to 0, y equals to 0, if you put it here, this is 0, this is 0 and this is 0. So you will get C1 equals to 0. The constant integration constant equals to 0. So you have the equation y equals to C theta. Okay. Now we apply this condition. If you apply this condition, put it here, y equals to L and theta equals to theta Ri. So what is C? C equals to L by theta Ri. So from this you can say that here we have written C equals to L by theta Ri. That means now y equals to C into theta. C is here we have obtained L by theta Ri. So y equals to L by theta Ri, okay, to theta. So this is the displacement equation. Now we have the relation between y and theta. So we obtain this function y equals to f theta is nothing but this one. This is the displacement equation and this is valid within 0 to theta Ri during rise. Okay. If you take derivative of that, theta dot equals to L by theta Ri into theta dot. Obviously, this is a constant. This is the uniform velocity motion of the follower. Now, if you take another derivative of this, so this is constant. That means this is equals to 0. What about jerk? If you take another derivative, obviously that is equals to 0. But just consider the motion. There is a dwell. Before rise, there is obviously a dwell. And then suddenly there is a uniform velocity. So from 0 velocity to uniform velocity. So at this point, what is the acceleration? There is infinite acceleration because there is a discontinuity in velocity. You have a 0 velocity, suddenly you want a constant velocity with some magnitude. That means there is a discontinuity which needs acceleration, which is very high acceleration. If very high acceleration is there, that means there will be very high inertia force, which is not good for our system. So we need to make some kind of correction here. So we make the cam such that so that this discontinuity should not be there. We'll discuss this tomorrow once again. Since you have classes from 9, I am stopping here and we'll continue in our next class. Okay. Thank you. If you have any question, you can ask me. Any question, any doubt?
Sir,
Hmm.
so nowadays for better performance, in many places cam follower systems are changed by electronic systems.
Right.
So is it better or not?
No, obviously it is better. But sometimes, electronic system has some advantage. Electronic system has some disadvantage. In some applications, cams are maybe still good. Okay. What are the disadvantages of a electronic system? Disadvantage is for electronic system, every component takes a time to do the calculations. Do some signal is there to process the signal? It takes some time, very small fraction of second. But we need a real-time response. In the real-time response, when it is doing those calculations and processing the data, a very fraction of second should be missed by this electronic system. But for a mechanical system, it is not possible. Okay, that is the advantage. Advantage of cam follower mechanical system over the electronic system. But obviously, electronic systems are necessary nowadays. Only those systems are there. But what another thing I want to point out here is you need to know these principles. If you know these principles, then you can design your electronic system.
Sir, temperature variations cannot be resisted by electronic system is also one issue.
Temperature?
Like electronic systems can't work at high temperatures or very low temperatures.
So
Failure
that is
tendency
also,
increases.
yeah, those are the challenges. But nowadays, people also designing materials where can they use this electronic system also. Okay, those are the challenges. But challenges are there, then only we are earning our bread and butter, right?
Yes, sir. And
Fine.
sir, in this cam follower, the springs also take a small time to send the force back,
Mm-hmm.
send the energy back.
Mm-hmm. No, I'm not getting your question.
Sir, I'm saying that I'm pointing out that in normal conventional cam follower mechanisms with
Mm.
negative cams,
Mm.
they also use springs, and springs also take a fraction of time to send the energy stored back into the system.
No. It's not like that. Spring is always there in action, and it is ensuring there is always in contact. Okay, there is no delay. It is always in contact. Only thing that you have to overcome this spring force when the follower is moving up and down. There is always the spring force. Okay, so in that case, they to over because there is a restoring force always acting. That means there is a frictional force acting between the cam and the follower. That frictional force you have to overcome. Okay, let me stop it here because you have classes. You go and attend the class. Okay, we will discuss this later. Okay, thank you.
Thank you, sir.
Sir.